three-way merge, and we'll prove a few things along the way. So what the diagram you see on the top right corner has two arrays, two halves of the arrays, if you will, right? L1 at the top, L2 at the bottom. And I will recreate the same diagram. So this is L1, this is L2, okay? And these are two elements assigned to processor PI. This is A, this is B, and this is also assigned to processor PI. From the second list, it is X, okay? And X is what we are considering as a candidate, like every other candidate, right? Without loss of generality. We pick one element of PI from the second list and figure out where it would have gone in the first list, okay? And so its rank is between A and B, okay? It also says that this is position I plus M times P, and this is nth thing in its I'm running out of space here now, so I plus N times P. Alright, so X is the nth element, or the element we have chosen in the second list is the nth element, and it happens to go after the mth element in the first list, the mth element being A. So can we say a few things? If we consider this element X, how many elements, knowing that it goes between A and B, right? Its rank is between A and B, or its rank is the number of elements PI has. What is its rank exactly? Knowing that it goes between A and B. So rank of X in L1.
A where it isn't.
A and B are adjacent in its strided pattern, so it goes between A and B. That's the main thing. Sorry?
Lying somewhere between A and B, so its rank in L1 will be A and B plus I plus whatever, how far it is pointed.
Exactly. So within P1, its rank is M, right?
Within its
Is it? M plus 1 actually. Because, sorry?
M plus 1.
Yeah, P is its actual position, but we don't know its comparison with everything else.
Rank, we are talking about all.
No.
Only that.
We can't, right? Because we don't know its comparative value with respect to everything. We only have compared it to, or PI has compared it to A and B and other things which were P apart. And we have found that it comes after A. Okay, and A is the mth element within PI. That's why it's I plus M times P. PI starts at I, and mth element of I will be I plus M times P. Right? So the rank of this element X within the PI's section is M plus 1, right? Because there are exactly M plus 1 elements less than it. For the time being, let's assume everybody is unique, right? So X and A and B are different. You want to take an example? Suppose A is the first element. M is 0.
I
First element of PI. whatever I may be. Its m is 0, right? So that means there is one element less than x. Its m is 0 means there are 0 elements to its left. Right? If there are 0 elements to the left of a, then there are 0 plus 1 elements to the left of x, because x has everything that to the left of a and a. Fine? Okay. So the statement that we are going to prove is that what we are trying to do immediately as a sub step of that proof is to ask what is the minimum number of elements that have to be before x in the entire L1.
Is it
Not just for P1s,
Pi plus m.
PIs.
A plus M? I mean,
I plus m,
A plus MP, all the elements before A, right?
but there are more elements going to come. So we're going to first, we're not going to do the entire proof, we're just going to do the main parts of the proof. And there are three cases to consider. One is that there is an A and a B, right? X goes between a given A and a given B. The other boundary cases are is X is the first element, which means X is, there is no A, or X is the last element, with that there is no B, which are again special cases of the same argument. So we'll only consider the case 1, which is X lies between a value A and a value B. And so we want to know how many elements are going to be less than X, but it's turned out to be too small. This thing you never can tell, because it automatically keeps shrinking text until it fits, and so you don't get to read the actual value, actual font size of the text. It's readable, right? Good. So why does it say that it has MP plus I plus 1 plus NP plus I elements less than X? We know that every element that's less than A is definitely less than X. And so how many elements are there?
Position of
Sorry?
what is the position of A?
Position of A, which is
I plus and I plus 1. 1 is for A.
1 raised to the power A.
1 is for the A.
Oh, 1, sorry. Okay, I got confused. Yes, plus 1 is for A. You want to know how many elements are to the left of A, and to that you add 1. Those are definitely less than X. Are there more that are definitely less than X? Some guys in L2, right? We know where X belongs in L2, it's nth position. So we know NP plus I elements are less than it. So just a little bit of massaging and it turns to the form M plus N plus 1 times P plus I minus P plus 1. Okay. It's probably easier to read than for me to read that out. Now we were going to ask how many numbers is at most, how many numbers are going to be less than X?
Question of
X may be just before B, right?
Yes. So all elements between A
all the
and B are
elements.
also
All those extra elements, that's it. And so you add that, you say M plus 1, because M plus 1 was the rank of B in its PI, times P plus I plus NP plus I. And the idea of putting the top thing in a given form was to make its form similar to the bottom thing. And what do you notice?
P elements extra.
One has I minus P as its second term, the other has just I as its second term. Okay.
P minus
So there are at least that many minus P elements less than it, and at most that many elements less than it. Where is it actually going to be? If we are going to sort it, we know that it is no. When we merge it in its original position, merge for the positions of pi, then n elements are going to be less than it, m elements are going to be less than it, right? N elements of the second side, m elements of the first side. So m plus n plus 1 is its position in pi. So m plus n plus 1 times p plus I will its be position when pi merges it. That's where it's going to place it. So it's going to place it at a position that is at most p away from its final position. Okay, it's not only at most p, right? It's actually I or I minus 1 or I minus 2 or up to I minus p, but never I plus 1. So x, wherever you place x, its final resting place could be that or any element up to p before it. But then why did I say if you see the other way, right? If you take an x on the other side, then you're going to come up to the same conclusion. And so any element in general will either be within p of its left side or within p of its right side. And so that is one process solved. This second diagram doesn't, it should have actually come earlier. Doesn't add too much to the discussion. It's basically saying that that is where it would have gone. In why it would have been placed after merging. Okay. Now I want to say that each block is sorted after merging. Right? I've just said that each element is within p of each other. Okay. So maybe we'll show you.
How we are concluding after we have found that at least these many elements are less than this and at most these many.
Yeah. So how do we know its final position? By knowing its rank, right? So we need to know how many elements are less than it. Right? If you tell me that 39 elements are less than x in the total list, and I know it's going to position number 39. That's its final resting place. I just don't know the rank, right? But if I tell you that the rank is between these two numbers, then you know its final resting place. Right? Somewhere in between those two, right? Now, when I'm trying to find its rank, what am I trying to do? How many elements are less than it? Right? So that's all I'm trying to do. Trying to figure out how many elements are possibly less than x. And so let me ask first, how many elements, what is the smallest number of elements that is less than x? Right? There are some elements we know definitely less than x.
Number of elements less than a plus
less than a and less than x. Less than a in L1, less than x in L2.
plus a.
Maybe no other element is greater than x, but that many elements are definitely less than x. That's the first number. Second number is, we know in L2 we definitely know x is in its sorted position, right? So in L2 only elements to the left of x are less than it. But in L1, everything to the left of b is possibly less than x, right? So x comes somewhere here. X could be at this position or at that position. That's it. So there are p elements from here to there. Is that clear to everybody? After we get this merge, claim is that each block is sorted. Right? Block is again every p. So we're looking at some arbitrary block I. Okay, and we are looking at two elements, consecutive elements in this block. And for this block to be sorted, x must be less than y. And let's just say that the number x we have picked is jth from the left in its block. It's a jth position within its block. So ith block, jth position within the block is the number we have picked, and y is just to the right of it. And we are going to have to prove, for us to say that block I is sorted, that x is less than y. Okay. Now there are a few things that you can immediately see. If x is the jth position, then who put x there?
Jth processor.
Jth process, right? Pj. If y is at the next position, then it's put there by pj plus 1. Alright? Can you now claim that every element that pj plus 1 has enough numbers to its left? No. The numbers of pj, for example x, have enough number to its left. That's the thing I want to prove. And so this goes without saying that every element that was given to pj plus 1 had a number less than it. Pj. Right? Pj had a number that was less than pj plus 1. Right? So pj plus 1 was picking here. So just to go back to this picture, pj, if this a was pi, let's turn it to j. All right. So a was assigned to pj, and a prime was assigned to pj plus 1. B prime was also assigned to pj plus 1. Okay. X prime was also assigned to pj plus 1. That's the way cyclic assignment works. So if you look at the elements of pj plus 1, every element of pj plus 1 has something less than it. That's all I'm saying. There's no magic here. So when you pick an element of pj, you're guaranteed to have some element less than that number. Okay? And that less than number is definitely going to pj. Right? So now the question is, does pj have enough less numbers for this to be true? Okay. Now, because it is block I, it is block I, which number is basically a transposition. Which number of pj plus 1 was y? Ith number, right? Block 0 gave everybody their 0th number. Block 1 gave everybody their first number. Block I gave everybody their ith number. So x is ith number of block of pj, and y is the ith number of block pj plus 1. Right? Nothing fancy? Okay. And every element, we just said this, every element that was assigned to pj plus 1 is greater than an element assigned to pj. And y was greater than the ith element assigned to pj. And how many other elements were assigned to pj that was less than y? Everything before x, right? Everything before x that pj had. How many things did pj have that were before x? pj had how many things before x? This is the ith block. I things, right? Because pj, where were we? So let's say this is since we are using x and y, let's just stay there. No, yeah, x and y, let's stay there. This x comes from pj, this y comes from pj plus 1, and how many elements are less than this y in x? X is definitely less than y, but everything less than x is also less than y. How many elements less than x? Right? X was, well, we are in L2 now, so it doesn't matter.
But to prove that x was less than y.
No, x was less than. Good question. Good question. We are not proving that x itself is less than y. That's what we are trying to prove, but we are not saying, we are not assuming that x itself is less than y. We are saying that there are. I was overloading x, and let me explain. Y is the ith element of j, j plus 1, right? Fine. Now, how many elements of j are less than y? Forget about x. The ith element of j and every other element of j before ith element of j. Okay? It just so happens that x is over there now, but whatever that element used to be. Okay? So I elements of pi are less than y. Fine? Okay, that's all we are trying to say. I element of pi are less than y. But what do you think x is? X is now, after sorting, the ith element that pj was creating. Right? Since there are at least I elements, there are exactly I elements less than y, and x is that ith element, x has to be less than. Okay? Simple enough argument. Alright, again, I'll repeat it here. We are trying to prove that x is less than y. We have just instead proved that there are sufficient number of elements less than y in this block. Right? How many is sufficient? I. If there are I elements that pj had that was less than y, and x happens to be the ith element after sorting, then x was less than y. And to make sure that there are enough elements that pj got that was less than y, we simply use the fact that every element like y that pj got had a corresponding x to its left. Okay, again I'm overloading y, but corresponding assignment to its left. Okay, think about it. We are out of time, so we can't complete the proof yet. We'll do that on Thursday.
Does the argument not have anything to do with L1 and L2?
This is for any block coming in L1 or L2, because the same argument holds. Right? We are just picking every ith of L1 or L2. So this has nothing to do with L1 or L2. So a block is sorted, and an element is within P of its position, which means an element can be going to the next block or to the previous block, nowhere else. Okay, so there's a little bit of more stuff to tie up our loose ends before we finish. Are there any questions? We were trying to merge two sorted lists. In this example, it's L1 and L2. And the algorithm was to take every odd element from L1. No, this is P-way merge. So every Pth element from L1, every Pth element from L2, and one processor is going to merge that. You have another set of Pth from L1, another set of Pth from L2, and so on. So P processors each are going to be merging it in parallel, and at the end, and they're going to do this in place, right? So 0 and P minus 1 and 2P minus 1 will now be sorted across from between L1 as well as L2. And then we do 2 steps of sorting between groups of P. Right? So the first block of P and the second block of P gets merged, and then third, fourth in parallel is getting merged, and so on. And then we do one more step of leaving the 0th alone, merge first and second, third and fourth, fifth and sixth, and all of those happen in parallel. Okay. And one of the things we already saw was that elements will be within P after this, the first step. When you have taken every Pth element has been taken by processors and merged. We also saw that every block is going to be sorted. Okay? So after the first step is done, when you go back and look at the chunks of P each, they are all going to be sorted. So we're going to skip through those blues. Does that complete the proof? This is where we were at. Does it? Yes, we do.
Yes, we have. Even I didn't. Sorry.
No, we do have to continue from here. But the question is, are we done? Meaning,
Okay.
the two things we have proved is that within each block, one is that elements are within P of each other. And the second is that within each block, they are going to be sorted. So now the question is, after step 2, are we done?
So initially also the lists were sorted.
Yes.
So now just placing them contiguously won't it be the sorted list, final sorted list?
But the left list and the right list was not sorted with respect to each other.
That's what it
Left list was sorted, right list was sorted, and then we have merged the even ones, merged the odd ones, right? I keep saying even and odd because it comes from batchers, but we have merged every pth, right? So the blocks that we have generated after the merger, every element in the block came from a different merger, right? And so there is no guarantee that it is, well, there is of course, but we have to realize it, we have to prove it.
Yeah. Okay, fine, I can understand. But the second elements were always more than the first elements. The first list had all the first chunk of P elements. They were always smaller than the second chunk of P elements.
But may not be from this.
Not but from those elements which come from L2.
From the other list, they may not be the holding same property.
Right.
So we need one scan through the resultant list, I guess. Is one scan of adjacent pairs.
Not just adjacent.
No,
Oh, you mean
I mean
adjacent
the
blocks?
Adjacent blocks.
But adjacent in both ways.
Both
Adjacent
ways.
in both ways,
Adjacent left and right both.
right? So that's what the second step was doing. Second step said, so we've established that each of these blocks of P, it's better to talk in the context of a picture, and let's go through that. We had generated that proof B slide said that if we look at these blocks of P, we know that each is sorted. Each block of P is sorted. We don't know whether all of this is less than all of that, right? Or for that matter, less than all of the remaining ones.
Then what does that mean in the claim number 1?
Claim number 1 in this line.
Yeah.
So it's after the 2 steps are done.
Yeah.
After the 2 steps, meaning the first was the division and then the first merging step. It says that the block I any element in block I cannot be greater than elements in block I plus 2.
That is the same claim as
each element's actual target position is not P away more far away than P.
Right. So basically that's how you prove it.
It's the same claim.
It's effectively the same thing. Yes. So we'll just quickly rush through this. We know that these two are merged. These two are going to be merged just like any other merge that we have talked about, right? Because this is sorted, that is sorted, individual each block is sorted. I just don't know if everybody here is less than everybody here. So I simply merge these two like any other two merged lists, two sorted lists being merged, and then we'll be done, right? Except that the other side may also have less than P or be in a position which is greater than some P positions, up to P positions after where it was supposed to be. Right? So you have to look at the left side also. So how would you prove it? And this is now kind of trivial after you realize that it's within P of each other. But let's go through the slide anyway. You essentially want to prove that the last element in a given block is less than the first element 2 blocks from now. This step is a bit more involved than just knowing that if every element is within P of each other, that does not mean that every element. So here the statement of this lemma, so if you wish, is if you look at elements in block I, then they are guaranteed to be less than elements in block I plus 1, I plus 2, right? That is not implied directly.
Yes, sir, because this element y can come in I plus 1 block and so can x.
Yes.
We can be sure
We
of
can't
that
say
it will
from
not
the-
lie in that index range.
So we only know that x may be within this place to that place. We don't know about other elements, right? Some other element that is in
May come to this thing.
block P or should have been in block I plus 2 is actually here, right? So, or I should say, should have been in block I plus 3 has reached block I plus 2. Okay, so you cannot claim that just because you are within P of it, your final position, that anything that is greater than P away from you is guaranteed to be greater than. And those two are different statements. So we do have to prove. So in this example,
So why do we need to prove that? You have to just claim what is the rank of x.
rank of x.
So we are very sure that rank of x will not lie in block I plus 2.
We know that, but we don't know about the current distribution of elements. Right? If everybody else was at their rightful place, then we could definitely say that x cannot be greater than any element in P plus. In fact, now then we could say even P plus 1.
The question is that why should I worry about the values in the blocks? I have identified where x is currently, and I have identified how much it can be varied, P left and P right. So I can talk in terms of index that it will not be lying on this index. It will be surely less than on this index.
Definitely.
So if I'm able to figure that, then why should I worry about whether?
No, the question is, for an element in block I, do we have to compare it against elements in block I plus 2? Right? We know that x is going to lie somewhere here, but if we have to pick one element from here, x has to shift one position to the right. It will still stay in the same block, but it may have to shift one position to the right.
I mean, can't you say that that block I, all elements block I are less than block I plus 3 for sure?
I plus 3 is definitely true, I plus 2 is also true.
Yeah, but if we just use I plus 3, then is it not only
Because you are only merging one to the left, one to the right.
Yeah, I mean, we can change that step and just work with the guarantee that it is just less than I plus 3, all elements in block I are less than.
No. That with the given algorithm won't.
Yeah, I mean, you have to maybe not do 2 but 6 merges, but
Yes.
constant.
I understand, but why do it
Yeah.
when you can actually, without anything else, you already know it's going to not be needed. Why would you do it? All right. So again, we're working in block I, or we have looked at an element X in block I, and we are trying to prove that X, any element in block I, is less than any element in block I plus 2. All right. Now we say, if we prove it for the last element being less than the first element, last element of block I, if we show that it is less than the first element of block I plus 2, then we can say this for everybody else, because we know block I is internally sorted, block I plus 2 is internally sorted. So the smallest of block I plus 2 is in the first position, the largest of I is in its last position. So if we can say something about these two, we've said the same thing about everybody else. Okay. So now let's look at where these things came from. X was assigned to all those elements that were assigned one in a strided pattern, right? Processor 1, processor 0, processor 1, processor 2, processor last, right? Processor P plus 1. And block I plus 2 was, the first element of block I plus 2 was given to processor P0, right? Just like every other first element of every other block, or 0th I should say. I hope I sometimes switch between 0th and first. I think the slides are consistent, but I may not always be. All right, so now if you look at the elements that were assigned, so if you look at the elements that are assigned to P0, right, they would be all of these first elements. How about the elements that are assigned to P minus 1, the last one? All the last elements? Every one of those last elements is greater than enough number of other elements, right? Because they are last in their block, and the block was sorted when we started. L1 was sorted, L2 was sorted. So if you look at those elements that were picked out by the last processor, P minus 1, every one of them had something to its left, which was given to P0. So all the elements to the left was given to P0 except
Border of the list.
the border of the list, right? The first element that P0 got was not to the left of a last element of another block, right? The L1, when the P0, that the first element of L1 was assigned to P0, was not after a last element of P minus 1. Similarly in L2 also there was one such right at the beginning. It was assigned to P0, but there was no P minus 1 to its left. Okay, so there are two such instances, one from L1, one from L2. So there are then remaining P minus 2 things that P0 had, which were less than what P minus 1 had. Okay? No? Why don't you try to say what I said?
Yeah, I mean, maybe trying to figure is easy.
So this convention hand waving is.
Yeah, I mean, figure this wrong actually.
So your left is our right, and we have to invert.
If you go back and look at the assignment, right, which was just alternating assignment, P0, P1, P2, P3, P4, P. Let's in fact, just so I can say it easier, let's say there are 16 processors. So P0 to P15. Okay, and there are every element has then 16 blocks, 16 elements. Every block has 16 elements, and P0 gets element 0, P15 gets element 15, P0 gets element 16, which is less than element 15 because it was sorted. L1 was sorted, L2 was sorted. So whenever you gave element 16 to P0, you definitely gave element 15 to P15. For every such P0 assignment, bar 2, there is a P15 assignment to its left. Okay? So that's all this is saying. That because of the 16 assignments that you made to P15, 2 of them didn't have this pattern, that P0 was followed by P15. Right? Sorry, P15 was followed by P0. Which 2 were those? The very first element. The very first didn't have anything to its left, so there's nothing that was assigned. So there are now 14 such pairs where what you get in P0, whatever you get in PP minus 1, P15, has a greater element in P0. Because every time you assign something to P15, you assign something lesser to P0. I say the opposite thing. Every time you assign something to P0, you assign something smaller, or maybe I said the same thing, just negated it twice. Every time you assign something to P0, there is a P15 to its left, and there are 14 of them. There is one pair missing. One of such P0s doesn't have a P15 to its left in L1. Similarly, there is one also in L2. Okay. So the other 14 of the 16 P0 assignments have a P15 to their left. Okay. So every P0 has sufficient number of P15s to the left. And what is the Y's position in its processor? Right. So again, coming back to the 16 processor example. So which element is Y for that processor? Y is given to processor P0. I plus second, right? It's block number I plus 2. Block 0 contributes the 0th element to everybody. Block 1 contributes the first element to everybody. You can see it, right? 2 contributes the second element to everybody. Right? So block I contributes the ith element to every processor. And so now this element Y that we are talking about is the I plus second element that was allocated to P0. Okay? And so these I elements, I plus 1 elements that are less than Y on processor number 0, most of them, right, bar 2, will have an element less than it on the last processor.
Basically, Y would have at least I numbers in P15 less than,
Yes,
and X is precisely the ith element making sense.
that is correct. Right? Which is precisely what the slide says. Which number is the position Y in its block, in its processor? I plus second, right? And so within the processor, things that are assigned to a given processor are in sorted order. So if I plus second element is Y, then I plus 1 elements are, no, its rank is I plus 2. So I plus 2 elements are definitely less than Y within its processor. Okay, and every one has an element less than it, right? Which was exactly assigned to P0. All those less than elements that we are talking about were assigned to P0. Right? And so the ith element of P0 you're right. Ith element of P15 is less than Y. But ith element of P15 is X, right? Because it's in block I, and so it must be the ith element of P15. Okay. Okay, I don't want to belabor this too much. The logic is not involved at all, but I think if I had drawn a picture that was more detailed than what I can do on the slides, it would have helped a little. But go back and think about it if you're still not sure. So this ith element is the element x, and so x is less than 1. Let's look at the 3 steps. Okay. Okay. So does division take time? Can be implicit, right? Basically, every processor with its processor ID will know where to begin, and it knows how many processors there are, so it knows what its stride size is. Right? Set and stride is all that is needed for it to logically construct its list. Okay. Now it has to merge 2 sorted lists, right? It's the things that it got from L1 were sorted, things that it got from L2 were sorted, but within them it has to do something. So for the time being, let's say it uses some third space to do some merging, but brings it back to this location. How long? N by P. Right? Each processor gets N by P from here, N by P from there, and it sequentially merges it. At the same time, another processor has got its own N by P. Everybody has got its own N by P. You sequentially merge it. After N by P time, you're done with that step. Then what remains? Now again, these blocks are size N by P, and you merge 0, 1, whereas somebody else is merging 2, 3, somebody else is merging 4, 5, P of them P pairs, precisely P pairs, N by P. Again, same thing for the last one. It may be one fewer, but who's counting? So total time that is being spent is N by P, which is optimal work-wise, right? Now this is, I also wanted to go through this specific algorithm because it is an example of something that doesn't strictly use the work time scheduling that we have seen before. It actually works very well. The merging works well. It is optimal. If you think just in bare terms, if you have n things to do, order n work was needed sequentially, p processors to do them with, n by p is as well as you can do. So asymptotically, right? Asymptotically, n by p is the best you can do. So this is optimal, isn't it?
If I look at, so I had 16 processors and it was taking me 100 seconds to do it on one processor, so I would expect 100 by 16 for it to take on 16 processors. So saying that I cannot do better than L3, right?
Actually, it will be better than 16 times 3. Moreover, if you have 1000 processors, it's not going to look as bad.
But I'm saying I invested like 3 more processors, but the speed up that I got was P by 3.
P by 3. But in practice, it will be a little bit better than P by 3. Why? Assuming certain architecture things. Because now instead of having one big list for the entire processor, you have smaller lists to deal with. Right? So more locality within each one of them and a better memory performance. But again, yes, you're instead of merging everything once, you're merging everything 3 times. So in that sense, it is not embarrassingly parallel. But that's kind of a sidetracked issue. The main issue that I wanted to focus on was that it is optimal. The work-wise, right? It is taking linear amount of time, linear amount of work. But here we haven't really done the time analysis. We said n is equal to p squared, but then we are kind of hiding it. We'll talk about what happens if n is greater than p squared. But if you just look at the time in the work time sense, how long does it take? P is equal to root n, so it is root n, right? So time-wise, it's not doing that well. So here is an example of something that is work optimal, not very well in terms of time, but because it's work optimal, and we have established a much more equitable distribution of work, which is very local in nature, very sequential in nature. It works very well.
So, but given that sequentially we do it in order n in time, and then when we do it in parallel, we are getting order n by p. So, isn't it? I mean, the best we can do apart from the factor 3.
Yes, that's why we are calling it optimal.
So why do you want to call it? The time is not very good. I mean, that's the best.
I didn't say that precisely. I said if you look at the work time behavior, then you would come to the conclusion that it is n by root n, so it's square root n, right? Whereas you would like it to be something in the neighborhood of log n. In fact, we have seen before. Let's stop for just a minute.